ఫైవ్ డేస్ అన్నారు కదా ఫస్ట్ మనకు నెట్వర్క్ కాదు.
Good morning, everyone. I once again welcome all the participants for this 5-day FDP program on the future of computing, emerging technologies, and trends. This is the final day, fifth day program. Now, I request Srimati Manasa Madam to introduce the resource person of the morning session, Sri Y. Narsim. Please.
Thank you, sir. Distinguished guests, respected principal, head of the department, esteemed faculty members, and dear participants, a very good morning. I am Manasa, working as an assistant professor in the Department of ECS. On behalf of the organizing committee, welcome you all to this 5-day FDP on the future of computing, emerging technologies, and trends. I deem it an honor to introduce the resource person for today's session. Y. Narasimhulu is currently a senior research fellow at School of Computer and Information Sciences, University of Hyderabad, working under the guidance of Professor V. Chinnavenkaya. He is also a research intern at TCS. He completed his master's degree from the JNTU Anantapuram and his bachelor's degree from SKU. He has more than 7 years of teaching experience. He serves as a reviewer for the journals IEEE Access, Soft Computing, and Neural Computing and Applications. He is an UGC NET JRF awardee and 3 times UGC NET Assistant Professor holder. His research interests include clustering, classification, optimization, and deep learning. He has 9 publications in various journals and conferences. Thank you, sir.
Thank you, madam. Now I request Mr. Narsimulu to take over the session. Thank you.
Thank you, sir, and thank you, Mansa, for the introduction. I'll start sharing my screen. Can you all hear me? Am I audible?
Yes, sir, you are audible.
Thank you.
Yes, you are audible.
Sir, you need to make me the presenter.
Yes, it's been done.
I'm unable to share.
1 minute, let me check again. Can you please check again? It's been given. Yes, your presentation is visible, sir.
Morning, all. So,
This conference will now be recorded.
Good morning, all. So, today I'll be presenting on a topic called classification with minimal data. So, our objective here is to do classification with as minimum as possible data sets. That's our main objective here. Okay, so let's get start. So this will be the outline of my presentation. I'll basically start introducing what is data. So I'll be starting with very basic things, and later I'll get into the challenges, and later we'll see the solutions to solve those challenges. Okay, so I want you to bear with me for a few minutes because of this introduction. This could be familiar to most of the people, but I want to set up the environment here so that everybody understands what is happening later in the session. So I'll start with data. So data is a collection of discrete values, or it can contain continuous values. Discrete values, examples of discrete values could be date, okay, or it could be age. Okay, so data can contain date, data can contain age, and some other things that are discrete, and it could also contain continuous values such as height of a person. Okay, and say for example the time, or the time exactly not cannot be considered as the discrete, but sometimes it can be considered as discrete, and sometimes it can be considered as continuous. Okay, and so these are the things that the data contains usually. Okay, and when we collect these data in various ways. That could be using questionnaires, or could be using interacting with people directly. So there are various ways of collecting this data. Once you have collected this data is organized in some organizational format, and this organization is called as tables. So once the data is collected from the questionnaire or some observations, the data is collected in the form of tables. And when you collect this data in the form of tables and combine them all together, you call it as data set. Okay, so what does a data set contain? A data set contain columns, and also it contains rows. So we'll speak more about it later. So this data is organized into rows and columns, and we'll speak what is a row and what is a column in a few seconds. Okay, so mathematically data set is written in this format. So this data set is a set of examples and label pairs. So we contain, this is x1 is an example that is collected, and y1 is a label that is associated to this data, and we'll speak about what is a label later. Okay, so this is how the data is represented. So x1 represents the first instance of the data, or the first observation that we have made, and x2 is the second observation that we have made, and y1 is the label that is associated to x1, and y2 is the label associated to x2, and so on till xn, where n is the number of samples that we have collected. Okay, and the table, as we have discussed, when all these individual observations are grouped together, when they are concatenated, we call it as a table. And in mathematically writing it, we can represent this table as x. So instead of writing x1, x2, x3 every time, so we consider this entire thing, or we represent this entire data as x. And the dimensions of this data is, it's not so when we represent the data in table format, so each row contains some columns in it. Okay, and there are multiple rows here. So the number of rows is represented as n, and the number of columns is represented as t. And the values that are present here are real values. So that's the meaning of this notation here. And the reason why we the reason why we collect this data and place it in a table format is it makes the machine learning world to understand easy. So machine learning usually take the data in table format, hence we try to place it or we try to represent it in tables. And it's not that the ML algorithms need tables. So there is a mutual mapping between these two. So table format is required for ML. Okay. So machine learning is a field in artificial intelligence. So the reason, what does the machine learning do is, it is concerned with learning the data. Okay. So usually previously what we used to have is, we used to have rule-based systems. So rule-based systems, what they used to do is, if something has to happen, it is written in a rule format. Say for example, if this is the scenario, this is scenario 1, and take this decision. And if this is not the scenario, take another decision. So this is how the rule-based system works. But writing rules for complex systems becomes very difficult. Hence we want an alternative way to escape this rule-based system, or make this task of writing these rules easy. So we have machine learning systems. So what is machine learning system? So it is a study of algorithms that can learn from data. So machine learning tries to learn from data. It's not a rule based system, and it will try to learn from the data by itself, and it will try to generalize to an unseen data. So what does machine learning do? It will look at the data that is present with us, and later it will try to generalize it, or it will try to do some task on the unseen data. So we give some data, we'll ask it to learn, and later we'll ask it to, or later we'll question it how it has learned. So this is the basic task of the machine learning, and we'll see various machine learning tasks. So why do we collect the data in tabular form? The reason why we collect it is easy to work. On machine learning algorithms usually need tabular format of data, and so let us look at machine learning in various perspectives. So there are usually two perspectives for machine learning. One is the statistical perspective, or it is also called as a mathematical perspective of machine learning, and the computer science perspective, which the computer science we'll see what are the differences between these two, and the terminologies that are used in the statistical perspective and also in the computer science perspective. So in statistical approach, the concepts are seen in terms of statistics and probabilities. So we view them in the lens of statistics and probability. Okay, here the data is assumed to be generated by some unknown function. So in statistical perspective, it assumes that the data is generated by a function. Okay, and definitely there is some function that generates this data is an assumption. Okay, and with some added noise. So the data which we get does not, so when we have data here with some let us say x1, and we have a label y, so there is a mapping between these two, and x1 is generated from a function f. And the goal of machine learning algorithm is to approximate this function. So we do not exactly know what is f of x or what is the function f. Okay, so the machine learning algorithm has to learn what is this f, and where did this data come from. That's another way of putting it. So when we have x, okay, we don't know how this has been generated, but we absolutely know that this has been generated by some function f, and we want to know what is this function. So machine learning algorithms will try to estimate or approximate this function f by looking at x. So how do we represent it, or how do we understand it? So given some input variables, so this is our input data. So this, or we can consider it as x. When we have this input x, so what is the predicted output variable? So we need to predict output variable y. So when we can predict the exact value of y for all occurrences of x, then we can say that the machine learning algorithm has learned the function f, or it has identified what is the function f that produces this data, and also the mapping that gives us from x to y. So that's the statistical perspective of machine learning. So here we are trying to predict the new input data. Once it learns, it will try to predict the new input data. Okay, and here there are few things that we need to understand. So x is the input data, and y is called as the output variable, and output variable is hidden for us the later state, but initially y is given for us to make the machine learning algorithm understand what is x. And this can also be written as, so we have seen what is output variable, what is x here. Okay, these columns that are inputs are referred to as input variables. So this x is also called as input variables, and the group of input variables are also referred to as input vector. So these input variables are also called as input vector. Okay, and the data that we have here has dependency with the output variable y. Okay, so the input variables are referred to as independent variables, and the output variable is called as dependent variable. So the y is dependent on x. So how do we get y is based on the values that are present inside x. So there is a mapping from x to y. Okay, and y is called as independent variable, and x is the x is called as independent variable and y is called as dependent variable. So this function can also be written as, we are trying to find a mapping from the independent variables to the dependent variables. So in spite of writing this in this format, there is a shorthand way of representing this function. So we called this entire data as x. So now we are trying to find a function f by giving this data x, and we are trying to find learn this function f of x so that we can estimate what is y. So this we have already seen about this x. And the computer science perspective, there is a lot of overlapping between computer science perspective and statistical perspective. There we called the rows as vectors and the columns as variables. Now here we call the rows as rows itself, or the vectors are called as rows, or also they are called as observations because they are taken from some way, okay, that we've already seen, and we don't get into these details how this data is collected. So we are just calling it as an observation that we have collected. Okay, and row of data or an observation is also called as an instance. So we can call a particular vector as a row, or we can call it as an instance, or we can call it as an observation. But an attribute is called as a column here. Okay, and another name for the column is feature. So all these things are can be used in any way. When I'm speaking about these algorithms and about the data, I'll call sometimes the rows as vectors, and call sometimes the rows as instance, or sometimes I'll call the row as observation. Okay, and sometimes I'll call the columns as attributes. So, or I'll call them as features. So I hope there will be no confusion when I speak about these things in the future. And in the computer science perspective, the function is also called as a program here. So this program takes input variables, and the program will produce an output attribute. And the what is that we are trying to learn here is we are trying to write a program that will take this input attributes and produces this output attribute. And the both perspectives are same here. What we are trying to do is we are trying to approximate f, and here we are trying to write a program that will actually produce this output attribute. Or the accuracy is so good that we can produce exact outputs that what we have expected to produce. So machine learning algorithms are described as learning a target function. So that's what we have discussed, that best maps input variables to an output variable y. So we are trying to predict what is f, the function f, and we don't know this function because we don't know where did we get this data from, but we are sure that there is some function that will produce this data x. And see, we are trying to predict this function, and as I said, we do not know what is f here, or the function. If we had already known what is f, then there is no need of ML algorithms, because we don't know what is f. We are trying to learn this using ML algorithms. And of course, it is not so easy to learn what is f of x, because we'll see the complexity of finding this f, and why it is so difficult for us to estimate this f using ML algorithms also. And also there is an error associated to every input data. So when we try to estimate a function f of x, okay, there is a possibility that an error could happen. So when we say that an error could happen, it means that the function which an ML algorithm has found is not exact. It is just an approximation of f of x. So when we are trying to find f of x, we don't exactly find what is f of x, but we'll try to find f dash of x, which is an approximation of f of x. Okay, and the difference between this f of x and this approximation f dash of x is epsilon. That's what this means. And this error is irreducible sometimes, and not in all the cases. There are there are machine learning algorithms that can that can exactly estimate what is f of x, but there are techniques which do not find what is f of x, or there are many situations where we cannot find f of x. In that cases, we try to find approximation of f of x. And there are plenty of problems that we cannot find what is f of x, and the researchers try to find what is f dash of x, an approximation. In such situations, this error cannot be reduced, and this error is also called as irreducible error. So different representations make different assumptions about the form of the function. So one algorithm makes one assumption of f of x, and another algorithm makes another assumption of f of x. So there are multiple ways of representing this, and each algorithm will produce a different f of x. Okay, so we do not know this, and hence what we have to do is we have to try different algorithms and try to predict f of x that is close, or we try to find f of x that is close. Excuse me. So it is important for us to try various ML algorithms to produce this absolute f of x. Okay, we'll see various types of machine learning algorithms. I'll speak few of them, and the reason why I'm putting all this information is I need to get into the active learning, because say unless we know what are these algorithms, we do not know what is active learning algorithm. So we need to know why we require active learning algorithm instead of using these general machine learning algorithms. So there are different flavors of machine learning algorithms. One of them is supervised algorithms. So supervised learning involves training a model on labeled dataset. So these supervised models, let us assume this is the model. Okay, so this supervised model requires data, and also the actual observations that we have observed, and also the label associated to it. So we give x and y to this ML algorithm, and we try to estimate f of x here. Okay, so when we give this label y along with the data, then the type of learning is called as supervised learning. Okay, so each label data is paired with the label, and also the data, and also with the label. And the goal is the goal for the model is to learn this mapping from input and outputs, and generalize to the unseen data. And the reason why we try to generalize to the unseen data is we are trying to test how good this approximation is. And some of the tasks that we perform using this supervised learning is regression task. So regression is nothing but predicting the continuous values. So the y can be discrete value, or it can also be continuous value. Okay, when we try to estimate this continuous value, then we call it as regression, and when we try to estimate the discrete value, then we'll call it as classification. And examples of such models are linear regression, logistic regression, support vector machine. This is not the complete set of supervised learning algorithms. There are more, but I have tried to put few. Unsupervised learning. So it involves training a model on data without label responses. Previously, we have given the ML model with X and also Y. Now we don't give Y, and we'll ask the machine learning model to just learn this X with irrespective of Y. Okay, and the goal for the model is to learn a mapping from inputs to outputs that can, sorry, this statement. So the tasks that can be performed on unsupervised learning is clustering. So say for example, clustering is grouping similar items. So say for example, there are this data set. Let us assume these points, these stars indicate some set of points, and these hyphens indicate another set of points. Okay, we don't have any label for it, so we don't say this star represents something or this hyphen represents something. So when we want to learn when there is no mapping between this input data and output data, then the machine learning algorithms try to segregate these things. So it will try to separate the data here. So this task is called as clustering task. So it will try to group the similar data items together, saying that all these points belong to one category and all these points belong to another category. You can name whatever it wants. So that depends on the task that we are trying to perform. And another way of representing is when we another problem that we generally see in unsupervised learning is dimensionality reduction. So when, as I've told you, there is a dependent variable and there is independent variables and undependent variables x1, x2, x3. So there could be variables that are not that doesn't map from this from x to the dependent variable y. So these variables do not have any importance here. So in such cases, we can remove these instances. Okay, so this task is also called as dimensional reduction. We are trying to reduce the dimensions here, or we are trying to reduce the number of features. Some of the examples of dimensionality reduction is k-means. So how do we perform dimensionality reduction here? We take only the centroid of this entire points here. So we say that this label, this particular instance will represent this entire set, and we take mean of this entire set, and we say that this particular instance will represent this entire set. So now we don't need all these points, or we just need 2 data points that represent this entire set of data. So this is one way of looking at the dimensional reduction in k-means. And hierarchical clustering is also another unsupervised learning algorithm. Okay, and PCA is also a dimensional reduction technique. So k-means is clustering, this is also clustering, and this is dimensional reduction technique, principal component analysis. And semi-supervised algorithms. So this fall between supervised and unsupervised learning. So here, what this semi-supervised try to do is, it will try to learn this data from very small amount of labeled data. Though there is, though we have enough sufficient amount of data, but we don't have labels for all the points. We have labels for only few points. We take only those few points and try to label, try to find the labels for other data instances. Okay, and the task that we perform on semi-supervised learning is clustering. Okay, say for example, let us take the same scenario here. So let us assume these are the points of one category, these are the points of other category, and we have used k-means here, and we found that this is how it has divided. Okay, and let us assume this point here, this point here, and this point here are not labeled. Let us assume these points are not labeled here. Okay, and only these points are labeled. So we take the mean of this point, and we see the label of this mean, or we don't. See, there are 2 ways of seeing. We know the label of this point, and using this we'll try to label all these other points. So we are trying to label the other points using the labels that we already have, and this can be achieved by using clustering technique. So this is one way of assigning labels to unlabeled points using very small amount of data that we have in our hand. So the tasks are clustering, classification, and regression. Example models are k-means, hierarchical clustering, and principal component analysis. So this is an example to show how clustering can be used to label using a very few amounts of labeled points. So another ML flavor is reinforcement learning. The reinforcement learning algorithms. Here they have an agent that learns to make decisions by performing actions in an environment to maximize the maximize some notion of cumulative reward. So when an algorithm, we'll talk about this. Or else, okay. So we have ML algorithm. So we give data to it, and we try to estimate what is the f of x here. Okay, when it, while learning the algorithm, we'll tell the algorithm what is the reward it gets for the correct prediction and what is the reward it gets for the wrong prediction. So whenever what does the algorithm do is it will try to maximize the reward. So when we add the final reward that it gets, it has to be as maximum as possible. That's the core objective of reinforcement learning. So the algorithm will try to maximize these correct labels that it is trying to find. So some of the tasks that can be accomplished using reinforcement learning is navigation, pathfinding, game playing. So every time an action is taken, a reward is being given. Or let us consider a chess game as an example. So let us assume this is the pawn that I wanted to move. So there are always rewards associated for every state that it is going to move. Okay, so there is a reward associated when it moves to this location, when there is a reward associated to move in this position. So every possible position that it can move is awarded with a reward. So the algorithm will try to maximize this reward. Okay, and the reward is associated with the advantage that it has when it moves to a particular location. So when this pawn is moved here, then there is a chance that it could kill some opponent object here. So then there will be more reward associated here. When it moves here, it doesn't kill any other object, so it will give us less reward here. So it will try to maximize this reward by moving to this location. So here we call this as a state. So it is right now in this state, and it will move to this state or this state or this state or this state or this state. So it has to take an action to move in one direction. So this is an example in gameplay, and also robotic control also. It depends on the actions that it takes. So examples of algorithms are Q learning. Here the action it is taken is based on the reward it gets. That's this algorithm which I have explained here is nothing but Q learning. When we try to do it using deep neural networks, then we call it as deep networks or deep Q learning. Okay, and policy gradient methods is so every time for every action we'll try to find, or at every step we'll try to find the gradient. Okay, and decide in which direction we want it to go. Here it is associated with the river, but here we call it as a gradient. So we take decision based on the gradient. And another flavor is online learning. So for all the algorithms which you have seen till now, the data is completely available for us at the desk for the machine learning algorithm to work. So we have X, and this entire X is fed to the machine learning model, and machine learning model will try to estimate this. But in online learning scenario, the data is not available at a time or all at once. So the data is available in the form of a stream. Okay, so online learning involves updating the model continuously as the new data arrives. So what does this machine learning algorithm do is it will receive X1 and it will update the model. It will receive X2 and it will update the model. So every time it gets the data, it will try to update the model. That could be a positive update or it could be a negative update. So where do we apply this? This is usually applied in dynamic environments where the data evolves over time. And some of the examples are navigation, pathfinding, game playing. So these are some of the examples. Okay, and tasks. And the examples are online gradient descent. So online gradient descent, every time we get an instance, the algorithm updates its parameters. Okay, so it updates the model parameters incrementally as new data point arrives. And passive aggressive algorithm, it updates only when the current prediction is wrong. So when the prediction is wrong, so how does this work? First, it will take X1. It will try to predict will try to predict the label of this. Okay, and if the prediction can be it can be correct prediction, or it can be wrong prediction. So when it predicts correctly, then it doesn't take any action, because the weights are correct for this data instance. And when it is wrong, it means that the weights have to be updated. Then it updates the weights based on x1. That can be using gradient descent or any other technique that helps in updating the model. And the other type of machine learning technique is active learning, and this is where we concentrate our remaining presentation. So I'll present an active learning algorithm. So I would prefer the audience to have a keen look at what is active learning. So active learning is a special case of supervised learning, where the algorithm can interactively query the user to obtain the desired output at new data points. So this is just as the semi-supervised learning algorithm, where we try to label where we have huge amount of unlabeled points, and we have very huge amount of very small amount of labeled points. And what we try to do there in supervised learning is we try to learn f of x using this very small data set, and predict the labels of this all unlabeled data set. Okay, in the same way, active learning also does the same thing. It will try to learn with the minimal data and predict the labels of the unlabeled data. But the difference between supervised and semi-supervised and active learning is there is an agent who is present here, who can guide, or who can tell us the actual labels of the uh, data set here. We'll look into it very clearly when we look into the problem. So the tasks here include image classification, object detection, and speech recognition. These are common topics what we have tasks that we have seen in supervised and unsupervised. And the algorithms that we use here are uncertainty sample, query by committee, expected model change. So we'll look at what these are later. And the other type of machine learning algorithm is federated learning. So it involves training learning models, or it involves training models across multiple decentralized devices. So usually the training happens everything at a centralized location, but here in federated learning, these are distributed across the network. Okay, and these devices could be edge devices. And these edge devices have a very small ML models that are running in it, and so there is a ML model running here. There is a ML model running on these edge devices, and once this ML model takes the edge devices also produce the data, so they get this data by themselves. They train this model, they train this data using this model, and send the weights to the centralized location, and centralized location will decide what to do with these weights. So some of the examples, some of the tasks that we see using federated learning is analyzing medical data and images from different hospitals. So these could be hospitals. They get the data, they train the model. So these could be the hospitals that produce the data here, and the hospitals themselves, they run some machine learning model on it, and they generate or they find some weights that are associated to this data, and these weights are transferred to the centralized location. So the centralized location will decide what to do with these weights. Okay, and this is an example of federated learning. So the algorithms that are used here are federated averaging. So each client trains a local model on its own data and sends the model updates to the central server, and central server will average these weights. So when we have, say for example, this is weight 1, I'm just taking one dimensional data here, considering one dimensional data, and W2 and W3. These data is sent to the centralized location, and the centralized location, it will try to aggregate this. So they'll try to find the average of these three. Okay, and the centralized location also has some data, and it will try to predict the data that it gets are also similar to what we get in this location. So it will use the weights that are obtained from here and try to predict. So other technique is while sending this data, in spite of sending this entire data to the centralized server and working there, the federated learning algorithm will ensure that the data is kept privately. Usually the federated learning approaches are used to keep the data as secure as possible. Instead of transmitting this data on a public channel, they'll try to use the data there itself and try and send only these weights in an encrypted format, so that the information is not leaked. Explainable, the next flavor is explainable AI. So it aims to make the decisions and behaviors of AI system understandable to humans. So when say for example, if an algorithm ML model will take a decision and say that the label of the algorithm is of the data instance is X, and here the previous algorithm whichever we have learned, it does not say how did it get to Y. So the only information that we have is weights, but it does not tell how did it get this weight and how did it come from x1 to y1. Here in explainable AI, it will try to tell us how did it get from x1 to y1. Okay, and the reason why it has to explain why it has come from x1 to y1 is to build trust, so that the humans can understand why it has generated this particular label to this instance x1, and also ensuring accountability and also enabling better decision making. So it has just randomly picked saying that the label of x1 is y1, then it doesn't mean that the ML algorithm has learned well. We need to know why it has labeled y1 for x1. So the tasks are model interpretation, providing insights into how a model makes decision. Okay, and feature it also tells us why each feature is important in making prediction, and also it helps us in debugging the models. Now let us get into the actual things. So the entire presentation will be completely on the classification. So we'll be doing classification task here using active learning. So we'll first discuss what is classification. We'll discuss the notation that we'll be using in this entire work, and also we'll see the actual algorithm. So what is classification? As we have described, it is a supervised machine learning method where the model tries to predict the correct label of a given input data. In classification, the model is fully trained using training data, as we have seen, and it is evaluated on the testing data before it is being performed prediction on new unseen data. So the prediction task can be discrete. So the classification algorithm can predict whether the value is a discrete value or it is a continuous value. When it is a continuous value, we call it as regression. When it is a discrete value, we call it as classification. And classification are of two types: binary classification and multi-class classification. So binary classification involves categorizing the data into one or two distinct classes. So the answers can be yes or no. It can be spam or ham. So these are some of the examples of binary classification. And multi-class classification, it involves categorizing data into one of 3 or more classes. So so suppose there is an image. So this image contains some objects in it. So we have multiple objects, object 1, object 2, object 3. So we say that this image has multiple objects in it, or we can also say that it has object 1 in it, or it has object 2 in it, or it has object 3 in it. So multi-class classification involves categorizing data into one of 3 or more classes. So each instance is assigned to one and only one class. So classification can be linear or non-linear. So linear classification methods assume the decision boundaries can be built, or can be a linear line. Say for example, these are all the linear classifications. Okay, so the data can be separated just by using a straight line. So for example, as we have seen earlier, let us take this data. So when we have a line that is separating these two classes, then we call this classification as linear classification. So this line is a linear line or a straight line. So the function that we estimate here is linear in other terms. So linear classification method assumes that the decision boundary that separates the class is linear. This means that the decision boundary can be represented as a straight line. Okay, it is called as a straight line in 2 dimensions, and it is called a hyperplane in higher dimensions. And nonlinear classification method allows for more complex decisions. So say for example, if the data is not separatable using a straight line, it has to be separated using using some curved line like this. Okay, so this is a non-linear function that we are trying to estimate. Okay, so non-linear classification methods allow for more complex decision boundaries that are not restricted to be linear. So they can capture intricate relationship between the features and target values. Is it audible? Is it clear?
Yes, audible, sir.
I changed my headset, so I'm asking. Thank you. So it so the data says that whether it is linearly separable or non-linearly separable. So linear separable data means that there exists a linear boundary that can be completely separate these data points, and non-linear separable data means there is no linear boundary that can separate this data. There can be only a non-linear boundary that can be that can separate this entire data. The model or a predictor is a function. So we are calling the model as a predictor here. A predictor is a function that when given a particular input example, it produces an output. Okay, so consider the output to be a single number. Say for example here in this scenario, okay, it is a real value here. This is how the representation looks later in our work. So in order to make it clear, I'm trying to explain this. So this is the function that we are trying to estimate, and this function, it maps the data x from of d dimensions to a real number, where the input vector is x and it is a d-dimensional vector, and all the values of this x are real numbers. So the examples of linear functions, this is an example of linear function, so f of x. So if there is a linear separable data and we are trying to separate them using some algorithm, it is trying to find this f of x, and if the f of x is linear, then this f of x looks like this, wx plus b, where w is the slope, so every line has a slope, okay, and b is the intercept of this line. And in the case of multiple variables, the number of variables here is only one variable, hence the linear equation looks like this. And if there are multiple variables, then the linear equation can be written in this way. Here w0 can be considered as the intercept, so this is the intercept, and w1, w2, wn are also can be called as slope here in this scenario. They are also called as coefficients corresponding to each feature. And we'll see the importance of this vector w here. We'll see why is it important for us and what is the machine learning algorithm doing here. We'll look at it. A nonlinear function is one of, and I want to make a clear difference here. I'm trying to speak about the classification here. This is linear classification and nonlinear classification, and here we are speaking about the data. So the data can be linearly separable or non-linearly separable. Okay, and we are speaking about the functions here. So the functions that we generate can be linear or non-linear. Okay, here we are seeing the linear functions, and here we are looking at the non-linear functions. Some of the examples of non-linear functions could be a polynomial function or exponential function, a logarithmic function or trigonometric functions. So any of these functions can separate this data. Okay, and all these functions are non-linear. So it can be something like this. So this is a non-linear function that is trying to separate these two sets. So as we have seen the representations here for linear functions, now we are seeing the representation for non-linear functions. Okay, so here these are the coefficients. Okay, and this is an intercept here, and these are the x values that we give as input to the algorithm. These are examples of non-linear functions. So when we give some data to the ML model, it has to pick either any one of these which can separate this entire data into multiple classes. Okay, so there are plenty of functions that can actually separate this data. It has to find one that can actually give us a good accuracy, or which can separate this data as neatly as possible. So the models, so now we are speaking about the models. There are linear models and also non-linear models. So examples of linear models are linear regression, logistic regression, linear discriminant analysis, perceptron, linear SVM are examples of linear models, and non-linear models, polynomial regression, decision trees, random forest database. So these are some of the examples of non-linear models. So when we have non-linear data, if you know that the data is non-linear, then using this algorithm does not give us good accuracy. Okay, so instead of using these algorithms with linear parameter in it, we can use these non-linear algorithms such that we can segregate the data as clearly as possible. So there is a high chance that these algorithms could give us good accuracy. Now let us look at the research gaps. So what are the issues with these algorithms which we have seen? So models often require a large amount of data, large amount of labeled data particularly, to achieve good performance. And what is the problem of getting this labeled data, large amount of labeled data? Collecting this labeled data can be expensive, and also it can be time consuming. So getting one instance of a labeled data can be very expensive, or it can take much longer time to get this labeled data. So hence getting labeled data itself is a hectic task, and also models often struggle with imbalanced data sets, and models are sensitive to outliers. So these all impact these factors impact the model. So the performance depends on these factors. Training models on large data sets can be computationally expensive. So computation is another problem here, and most of the models need the data to be available all at once, and this is also not possible in few scenarios. So these are some of the issues that we see in the general classification algorithm. So we'll try to address two of these challenges here. One is getting this labeled data is expensive, and what do we do in this kind of environment, and also how do we try to reduce the computation task when the data is large. So in order to understand the algorithm which we are going to present in the later stage, I want you to understand the terminology that is used inside this algorithm. So in order to understand it, I have put the terminology here. So X is the data set. It contains all real values, and the dimensions are n by m. So there are n rows and there are m columns. And each instance of X is called as xi, and it is an instance of X, and the I ranges from 1 to n, and the label of each instance is called yi, and the set of all the labels is called y. Okay, and H is a set of all possible hypotheses. So suppose there is some data that we need to segregate. So there are multiple functions that can separate this data. So all these functions are grouped and formed as a set, and this is called as hypothesis, and the set is called as H. And one among this hypothesis is called H. Okay, so H is a hypothesis that belongs to H, small h, and this is capital H. I want you to differentiate, and the error is represented here. So let us assume H is the function that we have estimated, and for xi it gives some label. Say for example, let us call it as y hat. If y hat is not equals to yi, which is the true label, so yi is the true label that we have, and y hat is the label that we have obtained. If these two do not match, then there is a mistake, and we are counting all the mistakes here. So for every mistake, we are summing it with 1. So whenever it gives us a wrong result, we'll add a 1 to the error count. Okay, and we are trying to reduce this error count. Okay, so when we have very less error count for some h, then we say that this has properly separated the data set. So this is the number of mistakes a hypothesis makes on the data set, and we are trying to minimize this. That's our goal here. So the ML model will take this data and it will try to estimate the function f of x. So learning f of x is nothing but it is trying to learn the weights. So W's, it is trying to learn these weights. So this is the most important thing to keep in mind. So the ML algorithm is learning this x is same as saying that the ML algorithm is trying to learn the weights of the function which we are trying to estimate. So f of x, we have seen f of x is equals to wx plus b. So this w is what the actual algorithm is trying to learn, and also this intercept b. And this is negligible, so we try to keep this away, and we try to concentrate only on w's here, the coefficients. So how does this work? Let us look at with a simple example. I'm taking a similar example every time to keep the things simple. So this is the function that the ML model has estimated. Okay, and we'll give one data xi to this model, so to this function. So f of x is equals to wx plus b. So we let us assume we have some weights w1 and w2. Let us assume we have two-dimensional data here. We have w1 and w2. Okay, let us assume this is 1 and 2, and we have x. This is 2, 1. We are trying to estimate this label of this x of I. So how do we do it? Is 1, comma 2 is dot product with 2, comma 1, and let us assume b is also 1 plus 1, which is equals to 2 plus 2 plus 1 is equals to 5. So the result of this operation is 5. If this value is greater than or equals to 0, then we call it, the label of this particular instance xi is 1, and if this value is less than 0, then we label this point as minus 1, or we call it as negative sample, or we call it as positive sample, whatever way we want. Okay, so we have now 2, comma 1. Now we are because the dot product of w and xi is 5, we label this particular instance as positive point. This is how it works. So the algorithm is trying to find these labels. So this is how the classification prediction function looks. So addressing the above gaps using the active learning, I'll introduce what is active learning, and also we'll see the algorithm that we are going to propose here. So as the digital storage gets cheaper and sensing devices proliferate and the web grows ever larger, it gets easier to get huge amount of unlabeled data. So we have plenty of unlabeled data that is available for us in the ways of speech, images, text, and documents, and so on. So we have plenty of unlabeled data, but the issue here is this data does not have labels associated to them. Because all this data is unlabeled and we do not know what do they actually mean, what do they say. For example, if someone uploads an image, we do not know what the image contains in it. If everybody posts, if anyone posts an image, he does not give us what this image actually contains in it. So we need to see what this image contains in it. So the data does not contain labels in it. So building a supervised classifier here will become a hectic task because we have very less labeled data. So in order to build a supervised task, what we need is we need labels. Okay, and obtaining these labels is very costly and also time consuming, and it is tedious and painstaking, and also requires expertise to label these points. So these are some of the issues with the data that we have. Let us take an example scenario here in order to understand why it is costly and also time consuming. So imagine you are a doctor analyzing X-ray images to identify potential cancer cases. Okay, you might have to review a large number of images. So the doctor is given huge amount of X-rays and ask him to say whether this particular instance has cancer in it or not. Because it is not the case that most of the people will have cancer. There are very few instances that the people will have cancer. So the task of identifying whether a particular instance has a cancer in it, it takes some amount of time, and identifying the labels for all these X-ray images is a very hectic task to the doctor. So you might have to review a large number of X-rays, many of which will be normal. So most of the X-rays here are normal, okay, and very few of them do contain cancer. So this can be time consuming for the doctor and also lead to fatigue. So the task is to label all the X-ray images that are present here. And how do we do it is the algorithm that we are going to see. So in order to do this, we have active learning algorithm. Look how this active learning algorithm will help us in doing this task. In active learning, the starting point is a data set whose labels are hidden but can be obtained individually for a price. Okay, we'll look at a simple scenario here. Let's look at the scenario here, the process of active learning here. So we have pool of unlabeled data. So this is unlabeled data. Okay, among this unlabeled data, we need to pick few points. Let us assume that initially we have picked this point, and this point has some importance in it. So out of this entire data, we have picked a particular point, and this point has some importance in it. And this point, the importance of this point is, it is difficult for the machine learning algorithm to label this point. So it cannot label this point.
for most of the points that are present here, it is able to label this point, but unfortunately it is not able to label this point. Okay, and so we pick such points, the points which the machine learning algorithm cannot label, and we give this label to an expert. So this person is expert. This person is also called as oracle. So we give this point to the oracle, and the oracle will give us the actual label. So because he is an expert, he'll give the right label for this point, and this labeled point is now added to our data set. So this is labeled data set now. So we pick few points from this data, and we ask the expert, and the expert will give us the label, and all these data is accumulated, and this entire data is given to the machine learning model now. So the machine learning model will try to learn the function that approximates this data, separates data. Okay, and again, because this is not sufficient, the data which we have is not sufficient, because machine learning models require huge amount of data. Using these points, we'll train the model, and because we have obtained a particular labeling technique here, we'll try to label all the other points, and we see how good the machine learning model has performed. Okay, so this process repeats until we try to label all the points correctly. So the difference between the semi-supervised and this active learning is we have an expert, and also there is a way of picking points which are very difficult for the machine learning algorithm to learn. So active learning is a machine learning algorithm that can perform better with less training if it is allowed to choose the data from which it learns. So we are giving the machine learning algorithm to pick its own points, because it will decide whether this point is easy for it or difficult for it to. And how do we say that a point is easy for it and difficult for it? Say for example, if this is the decision line that it has come up with, and let us assume there is a point here. The machine learning algorithm says this point is too far away, or this point is too far away from this on the right axis. So hence this point is a positive point. And if there is a point here, because it is too far away from the left axis, then we call it as the negative point. So it is easy for it to identify the point that is too far away from the segregator. But if there is a point somewhere here, and if there is a point somewhere here, and it is difficult for it to identify whether this is the positive point or the negative point, because it is very close to the decision boundary. This can be a negative point, and this can be a positive point sometimes. So we try to pick points that are very close to this decision boundary and ask the expert, because the classifier cannot say what is this actual label. So let us look at the active learning algorithm here. So initially we have unsupervised set. So we don't have label for the algorithm, for the data set. So first what do we do is we initially pick few data points, as we have seen in this diagram. So we pick few data points and we ask the expert, and the expert will give us the labels, and we add them to the label data set, and these points are used for the model to learn. So initialize a label training data set with a small number of representative points. So we initially pick few data points from this entire data set, and we label those points. So here actually we do not have an expert, so we assume that we get the label of this data point from the original data point. So our assumption here is we don't have an expert here, so we pick the labels straight away from the data set itself. So we have the unsupervised data. Okay, we don't have labels for it usually for the algorithm, but because we don't have an expert here, we are assuming that we have an expert, and we just get the data from the label point. Okay, so this is just an assumption here. So we don't have an expert, we just get the labels from the labels that we already have. So we are imitating an expert here. That is what I'm trying to explain. So initialized label training data set. So we randomly pick some data points. So how do we pick these data points is also an issue here. So we pick some data points, some small amount of data points, and we get the labels of these data points, and we ask the machine learning algorithm to learn these data points. So employ the initial data set to train a machine learning model. utilize the trained model to predict labels for an extensive pool of unlabeled data. So because we have learned from this small data set, now we try to label these data points for this huge data set that is already present with us. So calculate the measure of uncertainty for each prediction. So we have plenty of data points and we try to predict it. Okay. Now, while the termination condition is met, we repeat this process. As I have told you, we take few data points and this process continues until we obtain a good accuracy. So this is an example how active learning will actually help us. So let us assume this is the data set. These green points are positive points and red points are negative points. So this is the original data set with two classes in it. When we apply a logistic regression on it, okay, with few data, when we apply logistic regression on it, this is how the classification looks. So it is assuming that these points are negative points and these points are positive points. So these are the labeled points which we already have. We use logistic regression to label these points, and later, as I've told you previously, how do we pick a point that is that the model is uncertain? We pick a point that is closer to this boundary. So we pick the points that are closer to this boundary and try to find the labels of this using an expert, or try to get it from the labels that we already have and train the model later. So logistic regression is used to classify the shapes by first randomly sampling a small subset. So when we randomly sample and try to apply the logistic regression here, this is how the classification looks. But when we pick the points using active learning, and then when we apply logistic regression on it, this is how the points look, or the classification looks. So what is the intuition here? The main hypothesis in active learning is that if a learning algorithm can choose the data it wants to learn from, it can perform better than the traditional methods with substantially less data. So the assumption absolutely here is we have less data, and when we give the algorithm itself to pick what data points it wants to learn, then the algorithm performs better, is what it means. So let us see an example for it, which data points will the algorithm pick and which data points it does not pick. We will see three methods here. We will see a few examples. In active learning, there are typically three scenarios. So these are the three scenarios which we are looking at, in which the learner will query the labels for the instances. So one is membership query synthesis, stream-based selective sampling, and pool-based sampling. So these are the three techniques. We'll see each technique at a time. The membership query synthesis. So what does the active learning algorithm do is, the active learning algorithm will generate an instance that looks like the original instance of the data. So the algorithm first looks at the data set. It will try to learn the distribution of this data set. It will try to learn the distribution of this data set, and it does not pick a point that is inside this data set. What does it do? It will generate a sample data. Let us call it as X. Okay, and that this X is sampled from this distribution, and it is not present in this data set X. So for example, look at this diagram. It is trying to generate a image that contains 7 in it. Okay, so it is picking a data set that contains 7 in it. So it has seen many images that contain 7 in it. It has understood the distribution of this entire data set, and now it is generating a data X, generating a image that contains 7 in it. So this is how it generates the data. These data samples are very difficult for it to know. So it will ask the Oracle to label these points, whether this is 7. So it says that if it is very clear for it to understand that this is 7, then it will not pick this point, but it will pick point something like this. So it does not know whether this is actually 7 or not. So it will ask the Oracle that whether this is 7. Now the Oracle will decide whether this is 7, and this point is added to the labeled data set. Now it is very clear that a point that looks similar to this is also 7, or a point that looks similar to this is not 7. Now it comes to know that this is another way of looking at this data. Now this data is fed to the learner, again the ML model, and the ML model will again will use this information and label the other points. This is one way of doing it. Membership. This is called as membership query synthesis. And the other way of doing it is the learner will pick a data point, okay, and this point is picked from this entire data set. So this X belongs to this entire data set from the data set. So it will pick a point and it will decide. So should I ask this to the Oracle, or do I actually know what is this? So if it assumes that the data is or the point is difficult to label, then what does it do? It just asks the Oracle, and the Oracle will give us the label, and the label point is used as the training point. So this is another active learning technique. This is called as stream-based selective sampling. And the third one is it picks a point and it will directly ask the Oracle. So it does not take a decision here. It does not take a decision asking whether I should ask for the query or I should not ask for the query. So it will pick a point, it will directly ask. So it will pick few set of points, and these set of points are called as pool. So these pool of points are given to the Oracle to label. So hence it is called as pool-based sampling technique. Let us see few of them with examples. So which points does it pick and which points it does not pick? So these points are called the uncertain points, or the techniques that we use here are called measures of uncertainty. So there are 4 techniques that we'll be discussing here. Least confident technique is an active learning technique that will pick a point that the ML model is very less confident in labeling that point. So it is not able to label that point, hence it is picking this point. Okay, and there are 4 techniques that we'll see. We'll look at each technique with an example. So the first technique is least confident technique. So we have 2 data instances here, D1 and D2. Okay, and the machine learning algorithm has labeled these points like this. It says that the probability that D1 belongs to label A is 0.9, and the probability that D1 belongs to label B is 0.09, and the probability that D1 belongs to label C is 0.01. This is how it has labeled. So it indicates that it is telling that D1 belongs to label A. Okay, and it is saying that the probability that D2 belongs to label A is 0.2, and D2 belongs to label B is 0.5, and D2 belongs to label C is 0.3. So indirectly it is saying that it is less confident to label point D2, but let us see which point this actually picks. So if an active learning algorithm is employed with least confident technique, then let us see which point it picks. So the learner selects the instance for which it has least confidence. So it is here, it is very confident saying that D1 belongs to A, and the probability is 0.9. So it is 90% confident that D1 belongs to A, but it is not confident enough to say to which label D2 belongs. So it is saying that it is only half confident that D2 belongs to label B. So it is not confident enough to tell what D2 is, or what is the label of D2. Hence, it will pick D2, and this point is given to the Oracle now. So the Oracle will decide whether D2 belongs to A, B, or C. Now we have the actual label of it, and this is given to the learner, or this is added to the pool of labeled data set. Next is margin sampling. So previously what we have seen is we looked at the confidence level of the data point, or the confidence level of the machine learning label that it has labeled, and we have decided which one is less confident that we have given. But if you observe that it is here, if you observe that it is saying it is 0.5% confident that it belongs to B, and it is saying that it is 0.3% confident that it belongs to C. So the distance between 0.5 and 0.3 is very less here. But whereas if you observe here, the distance between the topmost probability and the next probability is very high here. It is very high here, the difference between the top probability and the second top probability. And here if you observe, the top probability and the second top probability distance is very low here. So there is a chance that this point could belong to B or this point could belong to C. So we don't know which point it, it has to take a decision based also on the second top value, because only taking the highest probable label is not sometimes very suitable. Okay, though in this scenario it is trying to pick D2, but it is also taking the second topmost probability that it has picked. It is also giving importance to it. The next is entropy sampling. In the entropy sampling, it will try to find the entropy of each probability that it has calculated for the data instance, and which one has the highest one, it will pick that point. So here it has calculated the probability, entropy for D1. So this is how we calculate the entropy for a particular instance with given probabilities, and we observe that this is for D1 and this is for D1 and this is for D2, because D1 is less than D2. I'll show you here. It also selects sample D2 here. And diversity sampling. So it samples items. The items which it is going to sample are very rare in the training data. So the points which usually occurred here are not picked here. It picks the points that are very rare, such as the points that are very diverse. So the idea is to cover the wide range of feature space here. So if all the points are centered at a particular location, and if there are very few points that are far away from this, it will try to pick these points so that it will pick wide range of samples here, so that it will learn this entire distribution properly. So an example of it is clustering task. So in clustering task, choosing representative sample from each cluster, so it chooses a representative. So say for example, if there are multiple clusters, so it will pick only one point, so that it will learn the diversification that is present inside this data. So it does not pick all the points that are present very close to each other, but it will pick only one point. So what are the challenges here? So the challenges that we are going to address are, one of the main issue with active learning is finding a way of choosing these query points. So it is not the algorithms which I put here are not the algorithms, there are many ways of doing it, and we need to find an efficient way of doing it, and this is not the complete list of selection methods or sampling methods. Okay, and we do not know which technique is efficient for us, and it is also required for us to build our own technique to find the uncertain points. So one of the main issue with active learning is finding a way of choosing the query points in an intelligent manner. Okay, so in order to understand these points, I'll briefly explain what we have seen earlier. So we have pool of unlabeled instances, and we need to pick few points from these unlabeled instances. So these points are called initial points. Okay, if the initial points are not good, then the machine learning algorithm may not learn properly. If the initial points are very good, then the machine learning algorithm learns this data properly, and it will help in further learning. Hence, choosing these initial centroids or initial data points is very much important. Okay, once we have a model, and selecting the points that are that the algorithm is uncertain is also very much important. So picking the initial centroids, the initial data points, and also picking the points which the algorithm is very much uncertain is an important challenge here. And also the algorithm, the machine learning model is made to learn from the pool of instances. So let us assume that in the first iteration it gets P1, this is pool 1, and the machine learning algorithm will learn, and in the second iteration it gets P2. So what should it do with P1 when it gets P2? Should it keep this P2 aside and train only on P2 is one question, or it should combine P1 and P2 and train next in the next iteration is the question that we need to look at it. So how does this model get updated when it gets the new labeled instances. So that's the question that we are trying to address here. So here we are presenting a solution, an active learning algorithm that solves the above challenges. Some of the assumptions that we make here is the data is linearly separable. That's the first thing that we are assuming. Okay, and it has only two labels. So it is a binary classification that we are performing, and in the binary classification we are assuming that the data is linearly separable. So there is a line that actually separates this data. So we don't need the non-linear functions that need to separate this data. And the model that we have chosen here is support vector machines. So the classifier model that we have chosen here is SVM. And in order to get into this, I want to briefly discuss about SVM first, and later get into the actual algorithm. So I'll briefly go through how support vector machines work. So an SVM is a powerful classification model. It tries to separate the dataset within two classes using a linear boundary. So this is also another technique that separates using linear boundary. And SVM tries to find a linear boundary that is located as far as possible to the points in the dataset. So it is trying to place. I'll show you the diagram in the next slide. And the kernel method in conjunction with SVM can help classify dataset using highly nonlinear boundaries. This we don't consider here, but I just wanted to say that it can also perform nonlinear classification. So let us take this scenario. We have two sets of points here, the red color points and blue color points. These two can be separated in various ways. So let us assume these are the lines which the 1 ML model has provided. So this is the linear line that 1 ML model has provided, and this is another line that ML model 2 has provided, and this is another line which ML3 has provided. Out of these three lines, which line do you think is actually separating these points? So if we assume, if you look at this scenario, ML2 has done a good work because it has properly separated. And how do we say that this has properly separated? When the points are, when do we say that this is properly separated? We'll look in the next slide. That will clearly give us what is the best line that separates this data points. So all the three lines separate the data well, but the second line is better, and we'll see the reason for it. So an SVM classifier uses two parallel lines. So SVM classifier, so say for example, all these three have been classified using SVM itself. So an SVM classifier uses two parallel lines instead of one line. Okay, so these two are the two parallel lines that the SVM has found to separate these data. So it tries to classify the data correctly. The first thing that it tries to do is it will try to classify data correctly. So it will assume that this point is positive point and these points are negative points. So it has to classify correctly. So that's one task that SVM has. Another objective of SVM is it also tries to space the lines as much as possible. So it is trying to deviate these 2 points, and it is trying to place these 2 points as far as possible. So it cannot just put these lines here because it is not proper classification. So it does not classify properly, and it does not even put the lines here like this because it is not separating these 2 lines properly. Because there is enough space here between these 2 lines and also the data point that is closer to this point, to these lines. So SVM has 2 objectives here. One is to classify the points correctly and also to place the lines as far as possible, such that there are see the lines are placed such that it also classifies correctly. So these 2 are dependent to each other. So we can visualize an SVM as the line in the middle that tries to stay as far as possible from the points. Okay, and this is very important for us to understand because we'll concentrate this area inside the algorithm which we are going to look now. Okay, and this is called as the margin. Okay, and these are positive points and these are the negative points. And the points that are close to this lines are called support vectors. So usually these lines are placed at the support vectors. So the SVM draws a line, and this line is very close to the support vector, and support vector is a point that is very close to this line. Okay, so this is also called as a support vector. This is also called as a support vector. So this is actually, this point will say that this is this point is very close to this line that separates with the negative points, and this point is very close to this point which separates the positive points. That's how it looks. So the error for SVM is, one is the classification error and also the distance error. So it has to ensure that the classification it does is classified correctly, and also there are the lines are as far as possible. And this is the actual separator. This is the linear function that it is trying to estimate, and the linear function, as we have seen, it is represented as f of x is equals to wx plus b. Okay, and see, if a point lies on this line, then we say that wx plus b is equals to 0. Okay, and if a point lies on this point, then we say that wx plus b is greater than or equals to k. So the distance between these two is k. Okay, and if a point lies on this, then we say that wx plus b is less than or equals to less than k. Okay, so these lines are called gutter lines, and this is the hyperplane which is actually separating the data. Okay, so just a small clarification. So if a point lies on it, then it is wx plus b is equals to k, and if a point lies on this gutter, then we say that wx plus b is a negative k, and if a point lies somewhere here, then this is true. Okay, and if a point lies somewhere here, then this is true. So this is minus k and this is plus k. And w is the vector that is perpendicular to the plane. So in spite of having some constant k here, what we do is we just normalize the data, and we'll ensure that the distance between the hyperplane and the gutter is only 1. Okay, so we modify that if any point x that satisfies wx plus b is greater than or equals to 1, we classify it as a positive point, and if a point x that satisfies wx plus b is less than 1, then it is classified as a negative point. And if there is any point that is somewhere here, then we call it as a misclassification. So we'll come back to the algorithm. So I'll just remind you what we have been talking. So what do we do here? We have pool of unlabeled instances. We need to pick few initial points, and these initial points are unlabeled points, and these points must represent the entire data set. That's most important thing here. So we have to choose initial data points and ask the human annotator or the expert to label these points, and we get the labeled points, and we add them to the pool of labeled points, and we train the model using the trained labeled points. And again this process continues. It picks another point here which it assumes that it is very uncertain. So once we have labels of it, it says that, oh, maybe this point I'm very uncertain, and it says that this point is very uncertain for me to label. So as the annotator, so we'll pick few points that are very uncertain, and again we ask the annotator which point, the label of these uncertain points, and ask the model to train on the labels that we have obtained later. So there are 3 ways of choosing these initial data points. So initially we have to pick few data points. We are looking at 3 ways of initial data point selection. One is random initialization. So we just randomly pick the data points from this unlabeled data. And another way of picking these data points is core set points and k-means plus points. So core set points and k-means plus, we'll look at them in a few minutes. So core set points. What is a core set? Let us assume we have some data. So a core set is a subset of input. So we'll have, this is a core set. Let us assume this is a core set. So core set is a subset of input such that we can get a good approximation to the original input. So the data that we have picked from these points is a very good approximation of the entire data set that is present here. So the core set points is a subset of the original data, but the subset is a very good approximation of the original input data. So the core sets can be computed in linear time. So instead of working on this entire data, now we can work only on this data and train our model. Okay, so this set is called as core set. So we use core sets as the initial data points for the algorithm to learn. Okay, and there are more intricate algorithms that can run on this sets. So we can run any machine learning algorithms on this core set data and prove that the results that we get on this core set are almost equivalent to the results that we get on the original data. So this is the original data, and this is the core set data. So the results that we get on core set data are almost close to the results that we get on the original data. So the models that are trained on these subsets are probably competitive in the results they produce with the models that are trained on the full data. So they both are very competitive in nature. I mean to say, like, the results that we get using core set are very close to the results that we get on the original data. How do we calculate the core sets here? This is how we calculate the core sets here. We calculate the distance of each points. We are summing the distance from each point to the mean of the data, the squared distance, and also for each point we are trying to calculate the distance. We are just normalizing here. Okay. So this is the formula that is used to find the core set points. Here we are allocating weights to each data point. So we are finding the weights for each data point. So a point that is far away is given more weight, and the point that is closer to the mean is given very less weight. Okay, so that is what this actually means, simply speaking. And after finding the weights, we pick k weighted points from the x. So we have the weights associated to each point. We pick the points, few points from this entire data set, such that the weights where each x has a weight 1 by k into q of x, where k is the number of points that we are trying to pick and q of x is the weights that we have attached or associated to the points. Okay, that's how the core sets are calculated. So in order to understand core sets, so that's the brief description about the core sets. So the points that are too far away from the mean are given more importance, and the points that are very close to the mean are given less importance. So this core set formula that we have seen here has two components in it. The first component is 1 by 2 into 1 by mod x. Actually, I forgot to put mod here. This is the norm of it. So 1 by 2 here indicates that we are giving equal importance to the length of the vector and also to the distance from the mean. So we are giving equal importance to the length of the vector and also giving equal importance to the weight or to the distance that it is from the mean. So we don't want to give one extra or we don't want to give this term extra, more weight and this term less weight. We want to give equal weights. In the second, that's what it means, and here we are calculating the norm of it. And here the second term is the distance between the point, the d of x, mu is the distance and mu is the mean. This is the squared distance. Okay, and we are summing all the distances here. This term normalizes the square distance of x relative to the entire data set. So that's the actual meaning of the second term. So the first term assesses the contribution of the data point based on its magnitude. So based on its magnitude, and this is given equal importance as I've mentioned. And the second term evaluates the contribution based on the square distance from the mean. And the distance from the mean and also its magnitude are given equal importance. The first term focuses on the size of the data points, while the second term focuses on the distribution relative to the mean. And this equal weight ensures that neither the size nor the distribution is dominant in calculating Q of x. And another, so this is one way of picking the points. So we ask this score set algorithm to give us few points, k number of points from this entire data set. So it will pick the points based on the distribution of this data. Okay, and these points are used as initial data points. So one way is by randomly picking the points. The other way is by using core set points. So this picks based on the distribution, this picks randomly. Another way is by using k-means points, k-means plus points. So the next way of picking the points is we are using k-means plus algorithm here. So the k-means plus actually what it does is it will try to cluster the data, but we are using the clustered centroids here as the points, as the initial data points for the active learning algorithm. So as simple as this. So how many clusters do we form? So we will form this entire dataset X into k clusters. So from each cluster we'll pick a point, and this point is used as the initial data point. So as I said, this is the algorithm that actually generates the initial data points. So generate samples. So if the method is random, it will generate n samples randomly, and if the method is k-means plus, it will generate k number of points from the k-means plus algorithm, and from courses it will pick k number of points, and these points are returned to the annotator or to the expert. So we are comparing the algorithm with multiple algorithms. So the first algorithm that we have used here for comparison is general SVM. So this is straight away working this entire data set. So we have this entire data set and give this entire data set to the SVM and ask the SVM to classify. Okay, so that's the first algorithm that we have used to compare. So this is a general straight away SVM algorithm. So as I have told you, picking the initial data points is an issue, and picking the crucial data points is also another issue, and also the computation it takes is also an issue. So we are trying to address these 3 points. We have seen 3 approaches here to pick the initial data points, and now we are going to see how we are going to pick these crucial data points, and also how we are trying to reduce this computational burden. So incremental active SVM is one algorithm that is trying to pick the data points from the entire data set such that or we are trying to pick crucial data points here. Let us assume this is the data. In order to understand this, let us look at the diagram here. So this is the initial data, original data, and this is how these two are separated. And among these data, we have picked a few points here. So these points, green color points, are the points that we have picked. Okay, and also the orange color points that we have picked. Sorry, only the green color points. Sorry. So we have picked green color points, and we gave the SVM to learn this data. Now SVM has drawn a line like this. So it says that these green points can be separated using this hyperplane, and also the gutters are these. So these are the gutters. So this is how the SVM has separated, and all these points are the points that we did not pick. So these points we do not know what are the labels. Okay, but for these points we know the labels. The green color points we know the labels, and the SVM has classified this rectangle is positive point and the circle is the negative point. Okay, and all these dashed lines are the points which we did not pick for the SVM to learn. Now we'll see how many points are present inside this margin. So we have this margin, and we'll see how many points are there here, and we select a k number of points from this margin, The SVM can clearly say that this point is a positive point and this point is a negative point because these two are very far away, as we have discussed. But it is very unclear that whether this point is a positive point or whether this point is a negative point. So it does not know the actual label of this because they are very close to the classifying line. So there are many points which the algorithm is very uncertain. So out of all these points, we'll pick the points that are very close to it. So we'll pick k number of points that are close to this hyperplane, and these points are given to the oracle for the labeling. So once we get the labels of these points, next we give this entire data set, the points that we have, green color points and also the orange color points, to the SVM, and we ask the SVM to classify now. Now SVM will clearly say that this point is a positive point and this point is a negative point. So this is how the SVM works in active learning scenario. Okay. So in order to make you clear understand, this is the original data set. Green color points are the points which we have picked using core set points or using k-means points. Okay, and these green color points are given for the SVM model to learn. SVM model has clearly classified these lines using these gutters and also the hyperplanes, and we find the points that are inside this margin, and among these points we pick the most uncertain points, and the most uncertain points are very close to the classifier, hence we pick k number of points from it, and these points combined with the points which we have previously labeled are given to the SVM, and the SVM will perform classification on it. Okay, again this process repeats, and again it will see whether there are any unlabeled points, these dashed lines inside this margin. If there are any unlabeled points, it will again pick k number of points and it will ask the oracle to label these points, and this process continues. So as I was telling you, we'll pick k points. And how do we know that a point is present inside this margin is another question. As we have seen, we call a point as a support vector when wx plus b, the absolute value of wx plus b is equals to k. Then we say that the point is a support vector. Here we can see three support vectors on this side, and this one as well, and this is another support vector here. They satisfy this equation. And how do we find that a point lies between the margin? If wx plus b is less than k, then we say that the point lies inside this margin. So it's easy for us to identify whether a point is inside the margin or not. So if wx plus b is less than 1, then we say that the point is inside the margin, and we pick the point, and out of these points we pick k closest points and we give the oracle to learn. When should we stop this process? So we take points here, we give SVM, again we check whether there are any points, again we ask the oracle, we check again, we learn. So this process has to be stopped at some point. So the stopping point are decided in this way. So when the classification accuracy reaches 100%, then we say just stop this classification. When the accuracy stagnation happens, when the accuracy does not improve, then we just stop this process. Or the size of the training set exceeds. So we have used all the points and there is no point left for the training, so hence we just stop this process. So this is the algorithm. So we generate samples using random points, core set points and k-means plus points, and we say the number of points that we want to find. Okay, and these points are appended to the labeled data set, and we ask the SVM to learn, and once the SVM learns, we'll try to find the support vectors. Okay, so here we are trying to find the support vectors. We are trying to find the margin points, and if the number of points inside the margin are greater than k, then we find the points that are closest to the hyperplane. If the number of points are between 0 and k, we select all the points inside the margin. So if there are more than k points inside this margin, then we pick only k points, and if there are less points, then we pick all the points inside this margin, and if there are no points, then we say that the SVM or we have properly learned the entire data set. So once we pick these data points, we get the true labels of it, and again ask the SVM to learn. So here what is that we are doing? In the first set we have P1 points. Let us call this as pool P1. Okay, and in the next iteration we get P2. Here we get K points. So we add this to the previous set and train this on SVM. So this entire data is given to SVM again to train. And later again we pick few K points and let us call this entire set as P2. Now we have P2 and again pick K number of points, add them and again ask the SVM to train. So this process continues. So the main issue that we should observe here is, so we have pool 1 and we are adding K points to P1 and this becomes P2 and this P2 is given to SVM again. So SVM is already trained on P1 and now we are adding this K points to P1 and we are giving it to SVM. So we are retraining SVM again on P1. So this burden of training again on P1 points is surely time consuming. So we try to address this issue and solve this issue by presenting another algorithm which is called active SVM. So active SVM will try to resolve this issue. So it does not train the SVM that is combined dataset P1 and K. It will train P1 separately and it will train K separately and then it will try to aggregate, as we have seen in federated learning. So a significant drawback of incremental SVM algorithm is at each iteration K nearest data points to the hyperplane are appended to the training set and the entire training set is employed for training purposes. So in spite of adding this K data points to P1, what do is we already have SVM that is trained on P1 and now we train this K number of points with a separate SVM and then we just try to aggregate this to get. So we have some weights here, we have some weights here, and we try to aggregate these two and get some new weights. And these weights, so what is that we are trying to avoid here? We are avoiding to train the SVM on these P1 points again. So if there are n iterations, then we are training SVM for on P1 points for n times. So it's not the actual n that we are representing here, the number of data points, it's just a number that I'm. So the second algorithm we propose, we look at the active SVM algorithm here. The active algorithm works in an active learning environment, and this algorithm is same as the incremental SVM algorithm. So the initial points are chosen randomly, or it can be chosen using k-means plus algorithm, or it can be chosen using course algorithm. So in spite of adding this entire points to the pool 1, K number of points to the pool 1, we just train them separately. Let us look at the scenario here. So this is the original. So we pick these green color points using core sets or K means plus plus. We pick the points, these green color points, and we ask the SVM to learn them. So the SVM has learned and it has separated these 2 points neatly using this hyperplane, and also it has found the gutters here. Now we search for the points that are present inside this margin. So these orange color points are the points that are inside this margin, and among these points we pick K points. Okay, now we have a SVM that is trained. We pick only these K points and we train SVM on these K points. Once we train this SVM on these K points, now we have weights here, or we have f of x, and we have f dash of x here. Now we try to combine these two. Now we get separate weights. So we have some W here, we have some W here, and we get new W. Now we can use this W to label the other points and find uncertain points, and this process continues. So what is the advantage here? The advantage here is we are not training these points again on the new SVM. We are training only the K number of points, and this will reduce the computation that it takes to train the SVM on all these points, green color points. how does this work? So to acquire the revised coefficients and intercept, uh, so just to remind you, wx plus b. So these are the coefficients and this is the intercept. So to in order to obtain this revised coefficients, so this update operation is used. Okay, so these temp coefficients are temporary variables. So these are the uh, old SVM weights. Okay, so we add them to the final. So it's just that we are summing them. That's the thing that we are doing here. So we have W, previous W, and we have new W, and we are just adding them. So these W's are also called as coefficients. So we are just adding the old coefficient with the new coefficient. So I'll just present the results. How so we worked on this. I'm trying to present the results as minimum as possible. So my idea was to present the idea. So we worked on all these data sets. We ran the previous algorithms on these data sets and show you the accuracy that we have obtained. So this is full SVM. The entire data set is trained on a single SVM, and these are the results. These are the accuracies that we have obtained. And this is incremental SVM. When these are the accuracies obtained when we have selected the points randomly, and these are the accuracies that we have obtained when we have selected using k-means plus plus, and these are the accuracies that we obtained when the points are chosen using core set points. Okay, and this is active SVM. So these are the accuracies when the random samples are chosen, when k-means plus plus samples are chosen, and the core set samples are chosen. I did not present the time. Actually, this active SVM has taken very less time comparing to the incremental SVM or full SVM. So full SVM has taken. It stands in second position. This one stands in the first position, and this stands in the third position because every time it has to work on it. So these are some of the results that I am trying to present here, and we observe that the accuracy has been pretty much good compared to incremental SVM and full SVM, and the core sets have performed really well when the points are chosen, initial points are chosen using core sets, then we have very good results. It indicates that what does this mean is the core set points are giving a very good representation for the entire data set. So when we have a good representation for the entire data set, then it is easy for the SVM algorithm to learn with very few points because it has only few points, and the few points are very impactful points, and hence the core set points have done pretty good work here. So, so what did we see till now? We have seen two active learning algorithms, which have used to perform classification task on minimal data set, and also try to reduce the time it takes for the model training, and also we also have seen a core set algorithm which produces the which produces the approximation of the original data set. And these are the references. Thank you. I'm done. If you have any doubts, you can please ask me. Sorry, I could not show you the code. Unfortunately, I did not put them on the public repository. So I assume there are no doubts. Thank you. Thank you for giving me this opportunity. And thank you everyone for your patient listening.
Are there anybody with any doubt, any questions, any queries? You can post. Thank you, sir. If there are no questions, we'll stop the session. Thanks a lot, sir. Afternoon session will start at 2 o'clock. Today afternoon we'll have valedictory function. See you again in the afternoon at 2 p.m. I request all the participants to join at 2 p.m. for valedictory function of this 5-day FDP program. Thank you.
This conference is no longer being recorded.